The average viewer sees browser-based robot control as a gimmick, a way to open a dashboard in Chrome with laggy video feeds, no different than watching a YouTube stream of a movement that arrives seconds late. The engineering reality is the opposite. Achieving sub-10 millisecond latency for high-bandwidth motor commands over variable internet connections requires bypassing traditional server-side bottlenecks entirely. This isn't about accessibility. It's about solving the control loop problem that has historically kept advanced robotics tethered to local networks or heavy hardware setups. The breakthrough lies in shifting from streaming video of a robot to streaming physics, where the browser becomes the real-time controller rather than just the viewer. For years, operating advanced robots required a dedicated control room with high-end workstations and local servers because the internet was too slow for real-time interaction. We used to think that if you wanted precise teleoperation, you needed heavy cables or expensive on-site computers running complex simulation engines like Gazebo. But recent research published in IEEE Transactions on Robotics demonstrates how modern web protocols have closed this latency gap to a point where a standard browser is now as capable of controlling a physical system as any custom-built desktop application. The key difference lies not in the software interface, but in what actually travels across the network. The fundamental hurdle has always been the control loop frequency. A robot must check its position and adjust its motors hundreds or even thousands of times per second to stay stable while moving. If you rely on traditional remote desktop solutions, the system compresses video frames, buffers them for smooth playback, and sends them back as a visual stream. This creates a delay where your hand moves in the browser, but the robot doesn't react until seconds later. That lag makes high-bandwidth control impossible, because by the time the feedback arrives, the machine has already moved into an unstable state. The new architecture changes this by treating the network not as a video pipe, but as a direct link for physics data. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This shift relies on three distinct engineering improvements found in recent studies from Shanghai University and related research groups. First is architectural offloading. Instead of sending raw video to a heavy cloud server which then processes it, these systems use an edge client model, where resource-intensive tasks like physics simulation are handled by dedicated nodes closer to the robot. The browser acts as a lightweight client that receives only state updates rather than entire frames of footage. This peer-to-peer connection bypasses centralized routing delays and allows complex kinematic feedback loops to run in real time without requiring high-end GPUs on the operator's end. Second is the transport protocol itself. The critical differentiator for low latency is the use of WebRTC, a standard designed for direct communication between browsers rather than traditional TCP video streams over HTTP. This reduces round-trip time to near zero, effectively synchronizing visual feedback with motor commands at frequencies required for stable control loops. Unlike remote desktop solutions that compress and buffer video frames, this approach transmits the state of the simulation or robot directly to the browser's rendering engine. The result is a decoupling of visualization from command execution latency, meaning you see what the robot sees instantly while your inputs are processed immediately by the edge node. However, software speed alone cannot fix physical instability. For high-bandwidth systems on jittery platforms, hardware-level perception becomes just as critical as network architecture. Research into adaptive lightweight LiDAR using MEMS mirrors shows how sensor geometry can be decoupled from robot motion at the physical level. By scanning fields of view independently via micromirrors rather than moving heavy sensors with the chassis or relying solely on software stabilization, robots maintain high-resolution perception even under vibration or wind. This hardware stability is a prerequisite for browser-based teleoperation. Without stable visual input, low-latency commands result in jittery control that can destabilize the machine regardless of how fast your internet connection is. The integration of these systems allows users to manipulate kinematic parameters like Denevit-Hartenberg matrices instantly within the web environment. Tools now available visualize URDF files directly in the browser, providing immediate feedback on feasibility before commands are sent to the hardware or simulation engine. This means you can test high-bandwidth control strategies from any device with a modern web browser without needing complex local installations. The data supports this rapid evolution. Analysis of specific publication histories shows significant optimization over time. One key paper was first submitted in February 2023 as version 1, weighing in at 35.3 megabytes. By the revised release in March 2024, that file size dropped to approximately 19.7 megabytes while improving performance metrics. This reduction reflects a move toward more efficient data structures and streamlined communication protocols essential for real-time operation. This changes the fundamental definition of robotics infrastructure. We are moving away from an era where you needed specialized hardware just to make a robot work remotely. The fear that web-based robots are too slow for precise work is unfounded when the architecture shifts from video streaming to state streaming via peer-to-peer connections. For curious viewers, this means democratization without compromise. You no longer need expensive local servers or complex software stacks to test high-bandwidth control strategies. You can do it from any device with a browser that supports modern web standards. The implications extend far beyond simple demos in a lab setting. This is the engineering foundation for future remote surgery, disaster response, and space exploration where operators must control physical systems across vast distances with zero perceptible delay. When an operator needs to manipulate delicate instruments on another continent or guide a rover through Martian dust storms, there is no room for buffering video frames. The system must respond as if it were sitting right next to the machine. This capability transforms the internet from a passive information highway into an active control plane capable of bridging physical distances in real time. The breakthrough isn't just about making robots easier to look at. It's about removing the physical barriers between human intent and machine action. By combining edge computing with advanced sensor stabilization, we have unlocked the ability for any web-connected device to serve as a high-fidelity control terminal. This is not speculative technology waiting in the wings of sci-fi novels. It is currently solving the hardest problem in physical AI, reducing latency to near zero for high-bandwidth control loops. The future of autonomous systems depends on this seamless integration where software, hardware, and network protocols work together as a unified whole rather than separate silos that fight against each other's limitations. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.